It's a great pleasure to be part of this eclectic group. I hope I'm not going to be too eclectic for you. I I didn't realize the motivation for this meeting, but a lot of those themes certainly resonate with me. My group has now contracted to almost zero, so my out-of-the-box scientific work really does rest explicitly on talking to people outside my field, and I'm very pleased to note that a lot of those key people in my life, out of the box life, are actually participants in this meeting. So I'm going to, in the next half hour, overview the free energy principle as it applies to the physics of sentience. This is going to be a breathless and classic talk in two senses. I'm just going to rehearse the kind of material that I would normally present to students and colleagues. So it's classical in that sense, but it's also classic in the sense that it rests upon a view of self-organization that inherits from classical physics. And I'm fondly hoping that towards the end of this symposium, Chris Fields and Mike and others may provide an alternative perspective, both from quantum information theory and other more biomimetic or biological perspectives. So I'm going to be talking about the physics of sentience. Just to overview this for you. Briefly telling a story as a physicist trying to understand self-organization with a particular focus on biotic self-organization. Much of this story rests on the notion of a Markov blanket and the ensuing Bayesian mechanics. I'm going to set that up very briefly and then tell exactly the same story in the language of a neurobiologist, specifically in terms of predictive coding and how they might be how predictive coding might be implemented in neural networks. And then if we have time, just turn to the next level of understanding this kind of self-organization in terms of active inference and planning as inference, and with a special focus on epistemics, seeking information to underwrite my self-organization. So this talk normally starts with a question posed by Schrödinger: how can events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? And what I want to emphasize here is the notion of a spatial boundary. And I'm going to read a spatial boundary as something brought to the table in statistics, namely a Markov blanket. So for those of you not familiar with a Markov blanket, it's very simple. Imagine we had some states of a little universe here, and I'd identify the states of something, say me. The Markov blanket comprises a set of states, specifically my parents, my children, and the parents of the children, that effectively insulate me in a statistical sense from the rest of the universe. They individuate me in the sense that if I wanted to know how my dynamics, how my states were going to evolve, I would only need to know my blanket states, my immediate shroud or insulation. Technically, this means that the internal states are conditionally independent of the external states, given my Markov blanket states. I'm going to make a further move here. I'm going to partition the blanket states into sensory states that are that influence but not influenced by the internal states, and active states that influence but are not influenced by external states. So in summary, we've got a particular a partition, if you like, that defines a particle that is separate from its eco-niche, its heat bath, its environment, and that has particular states that comprise blanket states that themselves and the internal states that can be divided into active and sensory states. And this setup you will recognize immediately by looking at some of our favorite things. Here's a brain with internal states influencing actuators, autonomic reflexes that change the extrapersonal or internal milieu, that produce sensory changes registered by my sensory epithelia that cause dynamics on the inside, my internal states. And exactly the same setup can be found in a cell. So, for example, we have intracellular states that, say, influence the acting filaments that support the cell surface states that impinge upon the external milieu, producing sensory signals on the cell surface receptors, coupling back to the intracellular states. So wherever you look, you've got this particular partition of interstates that is defined by the sparse coupling between them. So what I want to do now is to ask you just to forget about the Markov blanket. And I'm going to very briefly introduce a fundamental dynamics that underwrites most of physics. And then what we're going to do is to put the Markov blanket back into play and see what emerges. So this slide is meant to capture the notion that for any given system that can have some characteristic states and is therefore identifiable as a system, we can write down, at least in our heads, the trajectory of the states of that system over time. So I've cartooned that here in terms of this set of trajectories. And the characteristic aspect of these dynamics, or this dynamics, is that I keep on revisiting states that I once occupied. So these states characterize me. Technically, they're a pullback attractor, the kind of states that my dynamics are attracted to. So this could be an oscillation in a dendritic component of a cell, or it could be me getting up in the morning, doing my emails, having lunch, and so on. The key point is you've got this attracting set which contains or constrains the dynamics to ensure that I keep on occupying recognizable characteristic states. And the reason I've introduced that is that we know a lot about the dynamics of this structure. And if I read this structure basically as a probability of you finding me in a particular state at any particular time, then I can understand this as a probability density. But if I exist in characteristic states, that density is in and of itself not going to change with time. And that's interesting because we have at hand expressions for how this density will change with time that can be expressed in terms of the motion, the flow of states, the dynamics, and the amplitude of random fluctuations here. But if I know that my density is not changing with time, then I can associate my flow, my dynamics, with this probability distribution and the amplitude of random fluctuations. This sounds a little bit complicated, but all it's really saying is there must be, if I have characteristic states, a set of constraints on my dynamics and my flow and the way that I move through any abstract state space. And I can write that down effectively as a gradient flow, a hill climbing or a hill descending dynamics on the log probability of you finding me in a particular state. So now, if this is true, it also has to be true of the Markov blanket partition. This is what I want to illustrate here. If this is true, then I can write down exactly these equations in terms of my internal states and my active states. And the story I want to tell is that this looks very much like perception and action. And indeed, we can start to ask, well, what would this look like through the lens, say, of an economist or a behavioral psychologist? Well, it would look as if both my internal states and my neural dynamics and my active states, my choices and my behaviors and the way that I move are all trying to maximize this quantity here, the log of the probability of some sensory states given me, the kind of states that attract me, literally those that are valuable to me in defining my characteristic states. I should note that what we will be doing is using a free energy bound on this quantity here, this quantity being basically the value of these states in defining me. And from that, we can read various interpretations in terms of reinforcement learning through to expected utility theory in economics. That's nice because the negative of this quantity is known as self-information in information theory, or surprisal, or more simply surprise. It just scores the unlikelihood or the implausibility of you finding me in a particular state. When read in terms of information theory, what we arrive at are things like the principle of maximum mutual information, minimum redundancy, and in virtue of this evidence bound here, the free energy principle. That in turn is nice because the average of this self-information or surprise is entropy. So all we are saying is that to exist in a way that I am individuated from my environment, it would look as if I am trying to minimize my entropy. And of course, that's the holy grail of things like self-organization and synergetics. And of course, if I was a physiologist, this would just be homeostasis, keeping my states within viable bounds. There's a final perspective that I want to leverage, which is that of a statistician. This quantity would be read as the probability of some sensory data given me as a model of how my sensory data were caused. And that perspective affords an explanation or interpretation of this, this gradient flow in terms of the Bayesian brain hypothesis, evidence accumulation, and in particular, predictive coding. So that's the physics. The existence of a particle implies a partition of systemic states into internal blanket, namely sensory and active states, and external states that are hidden behind the Markov blanket. And because active states change, but are not changed by external states, they'll reduce the entropy of blanket states. So in effect, this means that my action will appear to maintain the structural and functional integrity of my blanket states. This can be read as, in chemistry, say, self-assembly, and a very elemental kind of autopoiesis or self-creation, or at least maintenance. Internal states will appear to infer the hidden causes of sensory states by increasing Bayesian model evidence and actively influence those causes. And that's what people in my world at least call active inference, emphasizing the inactive aspect of this. So now what I want to do is tell you exactly the same story, the same narrative, but using the language of psychology and neurobiology. This perspective, I think, has very, very deep roots back to the students of Plato, but nicely illustrated by this 16th century oil painter famed for painting still lives, that when viewed from a different perspective, give you a very different view. I'll have to do this by hand. So if previously you saw a bowl of fruit and now you see a face, the point being made here is that you made that face. This is something that you have brought to the table in order to explain this particular pattern of sensory impressions on your Markov blanket or your sensory veil. So this is very much, as Andy Clark would say, a sort of inside-out process as opposed to an outside-in process where sensory information is impressing itself upon your internal states and you are somehow extracting information. This is the converse, one of Dan Bennett's strange inversions, that you're actively creating this as an explanation or a hypothesis. And this notion probably best and most concisely articulated by Helmholtz. For example, objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous mechanism. So again, what it's saying, it has to be in mind as part of your internal states in order to explain or predict or make sense of the sensory impressions, so that you're using sensory information really to revise hypotheses or fantasies about what might be causing your sensory input. And this notion is clearly very closely related to the ideas of Richard Gregory in terms of perception just being hypothesis testing. These ideas have been used to great effect in machine learning. So for example, people like Geoffrey Hinton and Peter Dayan created a Helmholtz machine inspired by this Bayesian perspective on this kind of self-evidencing or maximizing model evidence, borrowing ideas from quantum electrodynamics, specifically this free energy formulation of this log evidence, this quantity that underwrites the dynamics in terms of this gradient flow formulation. But let's just come back to this producing impressions on the nervous mechanism. So from the point of view of the Markov blanket, what this says is, it looks as if I am compelled, or my internal dynamics are compelled to try and make sense of these shadows on my sensory veil, on the sensory partition of my Markov blanket, a sensory screen that I cannot see through, but I can certainly, and indeed I would be obliged to, if I exist, try to make sense of them. So asking the question and answering the question, what caused that? So how would that work in a brain? Well, we know how it works from the point of view of the underlying dynamics, because we know it's just a gradient flow on this log evidence, or the free energy bound on the log evidence. So I've just written that down here, say this rate of change of my internal dynamics, encoding, say, expectations about the causes of my sensory impressions, can be expressed in terms of this, what's called a Helmholtz decomposition of this flow here, with a gradient flow corresponding to corresponding to the flows that are driven by the random fluctuations, and a conservative solenoidal flow. I unpacked this a little bit just to motivate an alternative expression, which, if you're an engineer, you'd recognize as a Bayesian filter or a Kalman filter. So here's the conservative part, and here's the dissipative part doing the gradient flow. And I've just rewritten it down in terms of a prediction and an update, where the interesting bit, this gradient flow, this dissipative part, is a weighted prediction error. So what do I mean by prediction error? Well, imagine that I had a, I must apologize, my presentation is not behaving properly, so please ignore this bit here for the moment. Imagine that I had this sensory impression here, and I had some expectation, some belief that this was a howling dog. And if I had a generative model that could generate what I would see if this was a dog, then I could compare the prediction generated by my generative model with my actual sensory data to form a prediction error. So the prediction error, which is nothing more than the gradients of this free energy, is just the difference between what I sense and what I predict I will sense. So namely a prediction error. And then all this equation is saying is that I'm going to use my prediction error to drive changes in my internal expectations, if you like, representations, to provide a better account of what I am seeing in terms of minimizing the prediction error. And then this little picture would have normally been highlighted just to make the point that you never know what's actually causing your sensations. But if you can keep your prediction errors minimized for the duration of your life, then job done. In this instance, it was actually a cat, not a dog, causing my sensory input. So this is nice because we can now forget about all the physics and just say that the imperatives that underwrite both perception and action are all in the service of minimizing prediction error. And I've cartooned that here in terms of prediction errors being the difference between sensations and predictions. And I can minimize the prediction error in one of two ways. I can either change my mind by changing the neuronal states, my internal states, to make the predictions more like sensations. But I can also act upon the world to sample those kinds of sensations that are closer to my predictions. In other words, I can actively sample the world to realize my prior predictions in order to minimize the prediction error. So both action and perception in this instance are jointly in the service of just minimizing prediction error, or at least that is what it would look like. Here's a slightly more nuanced version of that scheme, just to illustrate the particular role of action in this prediction error minimizing process, or this gradient flow on variational free energy. Here I've drawn two different kinds of sensory inputs from the sensory screen. Here, visual inputs coming into the lateral geniculate that are passed forward to this visual cortex. the visual cortex is now sending top-down predictions to enable the computation of prediction errors that are driving, say, early visual representations. But these expectations themselves are in receipt of further top-down predictions, giving me secondary prediction errors that are then driving beliefs, expectations, Bayesian distributions over the causes of my sensations, and so on to any hierarchical depth required. But there's another kind of input, and here I've sketched this as proprioceptive input, say from my oculomotor system. This could come into, say, the pons. It could be compared with top-down predictions, and I could have a proprioceptive prediction error that could be used to revise my beliefs about how my motor plant oculomotor system is currently configured. However, there's a much simpler way that I can resolve these prediction errors by just returning them to the environment to activate certain muscles that are sending me the proprioceptive signals, so that the state of the motor plant then accords with my top-down predictions. And all I'm describing here is a classical reflex arc, where these top-down predictions are providing the set points, equilibrium, fixed points that specify where I think I should be looking in this particular instance. So just to make the point here that this inactive version of predictive coding is nothing more than just predictive coding with reflexes. So I'm going to close now just by giving you a couple of examples and just taking it to the next level by revisiting the structure of that Markov blanket. But first of all, let's just look at the ensuing control of as inference that you can simulate using these very simple dynamics. What we've done here is equip a synthetic agent with a generative model where she believes that there's some latent hidden dynamics, a central pattern generator, if you like, that is moving around an invisible point in her extrapersonal space. Furthermore, she believes that there's an invisible spring connected to this point in space and that it is pulling her finger around. So her top-down predictions are of two sorts. There's a proprioceptive prediction about what she should feel, and there's a visual prediction that she should see her finger being pulled around by this invisible point. So effectively, this generative model is making predictions that will enable, that are going to be fulfilled by action. And with this kind of simulation, you can generate quite plausible biologically or biomimetic kinds of behavior. Here's writing. And furthermore, with this simulation, reproduce a lot of kind of cardinal features of electrophysiology, certainly at the level of functional anatomy. So, for example, just looking at the internal states and interpreting them in terms of neural activity, we get sort of place cell-like activity with directional selectivity. And by removing the ascending proprioceptive prediction errors, I can simulate what it would be like to see the same consequences of my intended action, but not feel them, as if I was watching somebody else do the same thing. And of course, from the point of view of this simulation, it's no surprise that exactly the same neuronal dynamics are fit for purpose for explaining the same visual input, irrespective of whether I caused it or not. And the implication here is that we've got a mathematical metaphor of a very simple kind of mirror neuron activity. All of that rests upon this kind of architecture where we have our Markov blanket, sensory inputs come in, effectively we can read neuronal dynamics as maximizing the evidence for our generative models of the world in terms of Bayesian beliefs, subpersonal beliefs, that then provide predictions that enable action to resolve the prediction errors or look as if they are so doing through this gradient flow on the free energy that they can affect, which is just the proprioceptive prediction errors. And this provides, as illustrated in the previous demo, a fairly plausible but coarse-grained account of control of inference as inference and sort of reflexive behavior that is generated when we can create our own sensorium with the right kind of generative models. What I want to do is just to consider that Markov blanket structure again, and in particular, just ask what would happen if I was not able to read the active states from my Markov blanket. What would happen if there was no dynamical coupling or no connections between my active states and my internal states? And effectively what happens is that you can only now register the consequences of your action. But what also happens is that my actions now become a hidden cause. I can no longer see my actions. So they now become part of my model, a latent random variable, if you like, that is responsible for generating my sensations. And this leads to a much more sophisticated kind of control theoretic approach to sentient behavior, in which we have now a generative model that includes, as a cause of my sensations, my own actions. And this leads to the notion of planning as inference and active inference, where I now have beliefs about what I should be doing. And those prior beliefs are simply that I'm going to minimize the free energy or maximize the model evidence through my actions. And we can write that down explicitly in terms of this kind of hierarchical architecture, where now we've introduced the notion of an expected free energy following a particular action, and we can just follow through the physics. We won't have time to go into this, but I do like the sort of the mathematical symmetry between the way that a statistician would understand this quantity that describes the dynamics, internal and active, in terms of complexity and accuracy. If you were in machine learning, you'd read this as an evidence lower bound, where the bound is afforded by this KL divergence. If you now sort of rewrite this expression as it was emerged in the future, where the outcomes of my actions are not available to me, but they've now become random variables in the future. We've got a very similar structure, which effectively means I must, if I exist, and I cannot, and I can only see the consequences of my action, means that it will look as if I will always be trying to minimize risk and ambiguity, where risk is effectively the divergence of the difference between what I anticipate will happen if I commit to this particular action versus my valuable or attracting sets or the prior preferences that I have that are entailed by those prior beliefs. We can also read this in terms of a distinction between intrinsic value and motivation and preference-driven outcomes, and there being very close formal relationships with things like Bayesian surprise that underwrites what attracts my attention, the epistemic affordances that correspond to the expected information gain that I would get if I looked over there. And indeed, that's what I wanted to close with, just an illustration, a numerical study demonstrating this kind of behavior. So I've here created another agent. She is looking around a visual scene, but can only see foveally at least a small portion of that scene. And the idea is that because she believes that she's going to minimize her expected free energy or maximize her expected model evidence or evidence for her models of the world, she's going to score the quality or the probability of making a move, palpating the visual scene in terms of the expected information gain or the intrinsic value here. And you can work out the information gain that I would get if I moved this little searchlight from here, say, to here, and you could do it for all possible movements and create salience maps that look very much like those one observes empirically. And we can simulate this kind of behavior where in this particular instance, there was a very simple universe in which this agent lives. She can either be looking at an upright face, a sideways face, or an inverted face. But I repeat, she can only go and sample little parts of this sensorium at any one time and has to choose very carefully where to look. And here are the evolution of her salience maps or her expected information gain maps that change over time as she harvests or accumulates evidence and updates her beliefs until ultimately she reaches the right conclusion that she is looking at an upright face. So I'm going to close there and say everything that I've just said, but using the words of Helmholtz, who always manages to summarize things very succinctly. Each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we've understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial relations. And with that, it only remains for me to thank many of the people whose ideas I've been talking about, and of course to thank you for your attention. Thank you very much indeed.
Thank you very much, Karl. We have time perhaps for one question from the audience, if there is a question. Okay, do we have a remote question to ask?
Hello? Okay. We have a question from Wallace Marshall, and this was, I think, in reference to the Markov blankets portion of the talk. I'm used to states as being mutually exclusive, but that isn't the case here, right? Since different states apply to different parts of the system?
Yes, absolutely. Yeah, the states here are continuous states. It's an interesting question because you can actually rehearse everything that I've just said, but in discrete state spaces where then the states would become mutually exclusive, and the functional forms for these free energy functionals and expected free energy functionals actually become a little bit simpler and can be read in terms of the kind of choices and decisions that an economist would make, or that you could apply to psychological games and perceptual decision theory where things are discrete. It's either a face or a house, or I'm going to choose this or choose that. The maths is identical, but to connect it to classical physics, I've started from dynamics on continuous state spaces. It's a particularly interesting question because I'm hoping that Chris Fields at the end of this conference will give you the discrete quantized version of this, which would celebrate, I think, which is probably a more plausible way of formulating these states, which is in quantized, discrete, mutually exclusive states. Thank you.
Okay. Thank you very much, Karl. Thank you for participating remotely. We very much appreciate it. Thank you.